Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of simple numerical problems on basic concepts of electrical engineering. By solving these problems, we shall learn how to compute power and energy in context to an electrical system. Electric power is defined as the rate of change of electric energy P equals to W by T, where W is the electric energy. It is defined as the capacity of doing work. W equals to P into T. The voltage between any 2 points in an electric circuit is defined as the work done in moving unit charge from the point of lower potential to the point of higher potential. Therefore, W equals to V into Q and P equals to V into Q by T. Electric current is the rate of flow of charge with time. I equals to Q by T. Therefore, P equals to V into I. According to Ohm's law, V equals to R into I. Therefore, P equals to I square R or V square by R. For rotating machines, P equals to Td into 2 pi n by 6t, where Td is the torque exerted by the rotor in Newton meters and n is the speed of the motor in revolutions per minute. A conductor is carrying a current of 15 ampere for 15 minutes and the power absorbed by the conductor is 200 watts. We have to calculate the potential difference across the conductor and energy supplied to the conductor. Let us first write down the given data. Power absorbed by the conductor P equals to 200 watts. Conductor current I equals to 15 ampere. Operating time T equals to 15 minutes. Since 1 hour equals to 60 minutes, T equals to 15 divided by 60, that is equal to 0.25 hour. Let us now calculate potential difference across the conductor. V equals to P divided by I. Using values we get 200 divided by 15, that is equal to 13.3333 volts. Energy supplied to the conductor W equals to P into T. Using values we get 200 into 0.25, that is equal to 50 watt hour or 0.05 kilowatt hour. A 60 watt lamp is connected to 240 volt supply. We have to calculate the current it draws from the supply and the amount of electric energy used by the lamp in 10 hours. Let us first write down the given data. Power rating of the lamp P equals to 60 watts. Supply voltage V equals to 240 volts. Operating time T equals to 10 hours. Let us first calculate current drawn from the supply. I equals to P divided by V. Using values we get 60 divided by 240, that is equal to 0.25 ampere. Electric energy used by the lamp W equals to P into T. Using values we get 60 into 10, that is equal to 600 watt hours or 0.6 kilowatt hour. A resistor immersed in oil has 62.5 ohm resistance and is connected to a 500 volt DC supply. We have to calculate the current taken, the power in watts, which expresses the rate of transfer of energy to the oil, and the kilowatt hours of energy taken into the oil in 48 minutes. Let us first write down the given data. Supply voltage V equals to 500 volts. Resistance of the resistor R equals to 62.5 ohm. Operating time T equals to 48 minutes. Since 1 hour equals to 60 minutes, T equals to 48 by 60, that is equal to 0.8 hour. Let us first calculate current taken from the supply. I equals to V divided by R. Using values we get 500 divided by 62.5, that is equal to 8 ampere. Power dissipated in the oil P equals to V into I. Using values we get 500 into 8, that is equal to 4000 watts. Energy taken into the oil W equals to P into T. Using values we get 4000 into 0.8, that is equal to 3200 watt hours or 3.2 kilowatt hour. A 220 volt DC motor developed 8 kilowatt at 750 RPM. We have to determine the torque developed in Newton meter. If the efficiency of the motor is 88%, we have to calculate the current drawn from the mains and the number of units consumed if the motor operates for 6 hours. Let us first write down the given data. Developed power PD equals to 8 kilowatts, that is equal to 8000 watts. Supply voltage V equals to 220 volts. Efficiency of the motor eta equals to 88%, that is equal to 0.88. Speed of the motor N equals to 750 revolutions per minute. Operating time T equals to 6 hours. Let us now calculate developed torque. TD equals to PD divided by 2 pi n by 6t. Using values we get 8000 divided by 2 pi into 750 by 6t, that is equal to 101.86 Newton meter. Input power P equals to PD divided by eta. Using values we get 8000 divided by 0.88, that is equal to 9090.91 watt. Now we shall determine current drawn from the mains. I equals to P divided by V. Using values we get 9090.91 divided by 220, that is equal to 42.3223 ampere. Number of units consumed by the motor W equals to P into T. Using values we get 9090.91 into 6, that is equal to 54,545.46 watt hour or 54.5 54,546 kilowatt hour. A factory has a 240-volt supply from which the following loads are taken: lighting 300 150 watt, 400 100 watt and 560 watt lamps; heating 100 kilowatts; motors a total of 40 kilowatts with an average efficiency of 80%; miscellaneous various load taking a current of 50 ampere. Assuming that the lighting load is on for a period of 4 hours per day, the heating for 10 hours per day, and the remainder for 2 hours per day, we have to determine the weekly consumption of the factory in kilowatt hours when working on a 5-day week, and the current taken when only the lighting load is switched on. Let us first write down the given data. Supply voltage V equals to 240 volts. For lighting load, given total load P1 equals to 300 into 150 plus 400 into 100 plus 500 into 60, that is equal to 1,15,000 watts, that is equal to 115 kilowatts. Operating time T1 equals to 4 hours. Let us now calculate electric energy used by the lighting load. W1 equals to P1 into T1. Using values we get 115 into 4, that is equal to 460 kilowatt hours. Current taken by the lighting load I1 equals to P1 divided by V. Using values we get 1,15,000 divided by 240, that is equal to 479.2 ampere. For heating load, given power rating P2 equals to 100 kilowatts. Operating time T2 equals to 10 hours. Now we shall determine electric energy used by the heating load. W2 equals to P2 into T2. Using values we get 100 into 10, that is equal to 1000 kilowatt hours. For motor load, given power rating PO equals to 40 kilowatts, efficiency eta equals to 80%, that is equal to 0.8. Operating time T3 equals to 2 hours. Input power P3 equals to PO divided by eta. Using values we get 40 divided by 0.8, that is equal to 50 kilowatt. Electric energy used by the motor load W3 equals to P3 into T3. Using values we get 50 into 2, that is equal to 100 kilowatt hours. For miscellaneous load, given current drawn from the supply I equals to 50 ampere. Let us now calculate power consumed by this load. P4 equals to V into I. Using values we get 240 into 50, that is equal to 12,000 watts or 12 kilowatts. Operating time T4 equals to 2 hours. Let us now calculate electric energy used by the miscellaneous load. W4 equals to P4 into T4. Using values we get 12 into 2, that is equal to 24 kilowatt hours. We have obtained electric energy used by the lighting load W1 equals to 460 kilowatt hours. Electric energy used by the heating load W2 equals to 1000 kilowatt hours. Electric energy used by the motor load W3 equals to 100 kilowatt hours, and electric energy used by the miscellaneous load W4 equals to 24 kilowatt hours. Let us now calculate electric energy used per day. W equals to W1 plus W2 plus W3 plus W4. Using values we get 1584 kilowatt hours. Since 1 week contains 5 working days, total electric energy used per week equals to 1584 into 5, that is equal to 7920 kilowatt hours. So today we have solved a couple of simple numerical problems on basic concepts of electrical engineering. By solving these problems, we have learned how to calculate power and energy in context to an electrical system. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.